Friends, today we will discuss dynamic models of steam turbines and governors. So far we have developed the model for synchronous generator and the associated excitation systems. While studying the stability, we have made one assumption that mechanical input power remains constant, right. Now, while developing actually the model for transient stability analysis, right, where our swing equation is written in the form 2h divided by omega s d2 delta by dt2 equal to Pm minus P. Now, till now we have assumed that this mechanical power input is constant, okay, and this is a very valid assumption. However, whenever we want to do study involving some severe upsets in the power system, we want to know the long term, mid term and voltage stability analysis of the system, then the turbine and associated governor models are also required to be included. And today we will devote our studies to develop the models of steam turbines and associated governors. Now, before we develop this, let us look at this block diagram. This block diagram shows the complete power system. Now, you can identify here the different blocks. Suppose you start with actually the power system network. This is the block which shows the power system network, which represent the generators, transmission line network and loads. Okay. Now, from this network we get output as electrical power, and for the control of this power system as a whole we have different controls. Okay. Now, one control is actually the generation control, and for controlling generation what is done is that we sense the interchange power on various tie lines and find out the net interchange. We sense the system frequency. This is processed in a controller which is called automatic generation control, and the output signal which comes to the automatic generation control, right, will change the position of the speed changer. Okay. Then when you look the major blocks, we have the speed governor, speed controller mechanism and governor control valves and gates. Now, here we are writing valves and gates. The valves basically pertain to steam turbines and gates pertain to hydro turbines, and the output or the position of the gates, right, control the input to the turbine, and therefore this shows the turbine here. Now, we are while for representing the system dynamic model, what we do is that we represent the turbine separately, and then the output from the turbine will be represented as a mechanical power output, and this mechanical power output will be used to write the swing equation. That is, we will separate the turbine generator inertia and write the swing equation. So, that input to this block which we basically use to write the swing equation, we call it actually the turbine generator inertia. Input is electrical power and mechanical power. The difference of this is the accelerating power, and the output from this block will give you the angle, change in angular position and change the speed. Now, the speed deviation signal is processed through a speed governor. Therefore, the speed governor is a most important component in the control mechanism. It has two inputs, one coming through the coming from the terminal of the synchronous generator, and that is the speed signal. Another is the control signal coming through the AGC. We call actually the speed changer position. Okay. Now, these two signals, when they enter through this governor, governor will process it, and we have a speed control mechanism, and then ultimately the valves. Okay. Now, this is the complete schematic diagram which represents the location of steam turbine, the governors with respect to the total system. Now, our study will be confined to representing the steam turbine and the speed governing system. Okay. The reference material for steam turbine models and hydro turbine and associated governors is available in this IEEE committee report, because when we discuss the excitation system models, I have referred to a number of papers published in IEEE transaction and IEEE standards. Okay. Similar to the excitation system models, the IEEE task force on power system dynamics has developed the models for steam turbines, governors and hydro turbines and associated governors. This is published in the year 1973, and while developing these models, since this subject involves the mechanical system, right, along with the electrical system, right, and therefore, this is written by with the association of IEEE working group and American Society of Mechanical Engineers, right. Therefore, these two groups have contributed in developing the models which are published in IEEE transaction in the year 1973. This is a standard paper. I advise all of you to take a copy and read it. While developing these models, there are some assumptions which have been made, because when we see the system as a whole, right, we have contingency controls, for example, fast valving, right. Now, this type of controls have not been shown here in the models. We will develop these models actually and discuss these models from beginning. Now, to develop the model, what we need is basically the relationship between the input and output. Now, since here we will be dealing while developing the steam turbine model, right, where we know that the steam is generated in the boiler and then it flows through the various stages of steam turbine, and then ultimately it is exhausted to the condenser. Okay. Now, in order to develop the model, let us start with a simple steam vessel. Let us say that there is a steam vessel, and volume V is the volume of this vessel. In this vessel, the steam is entering, and let us say that QIN is the steam in kilograms which is entering per second, and Q out is the steam in kilograms leaving this. We will develop actually a transfer function model relating the Q out to Q in, and this basic model will be used to represent various stages of the steam turbine. Our basic objective is to develop a transfer function model relating the Q out, that is the stream coming out, to the stream coming in to the vessel. Here we make use of a basic equation which is called continuity equation. The continuity equation is written in the form d by dt of W. W is the weight of the stream. W is the total weight of the stream which is inside the vessel. Okay. This rate of change, this dW by dt is equal to V times d rho by dt. The rho here is the density of the stream. Okay. We can say that it is the weight in kilograms per meter cube. Okay. And V is the volume. Therefore, V into rho is equal to total weight. V into rho, that is the total weight of the stream. Therefore, rate of change of total weight of the stream content is equal to this difference Q in minus Q out. A very simple mechanism, that there is a vessel where stream is entering at a certain rate, stream is leaving at certain rate, right, and this difference will represent the rate of change of weight of the stream inside the vessel. Now, basic meaning of the terms here are: W is the weight of the stream in the vessel in kilograms, which is equal to V into rho. V is the volume of the vessel in meter cube. Rho is the density of stream in kilogram per meter cube, and Q is the stream mass flow rate. Q represents the stream mass flow rate kilograms per second. T represents time in seconds. A very simple equation. Now, here we will relate the rate at which the stream is leaving the vessel to pressure, right. Now, let us say that Qo is the stream leaving the vessel per second when pressure is Po, right. Therefore, at any other pressure, the Q out will be equal to Qo divided by Po into P, where P is the pressure which is different from the nominal pressure. Okay. P is the pressure of the stream in the vessel, Po is the rated pressure, and Q is the rated flow of the vessel. It means at a particular pressure the stream flow is Qo, and at any other pressure the rate of stream flow or stream flow is proportional to the pressure. Now, to develop the equation, we need actually the expression for d rho by dt. Okay. Now, to obtain the expression for d rho by dt, we can write like this: d rho by dt can be written as dp by dt, that is the derivative of pressure with respect to time, or the rate of change of pressure with respect to time, into d rho by dp. That this chain rule type of relation we have written, that d rho by dt is equal to dp by dt into d rho by dp, or you can put other way around, d rho by dp into dp by dt. That will be much better if you write down d rho by dt as d rho by dp into dp by dt. Then we substitute this expression in our continuity equation, we get Q in minus Q out equal to volume into d rho by dp into dp by dt. Okay. Now, here dp by dt can be replaced, dp by dt can be replaced from this expression. That is, you can write down, you can just take derivative of this equation. So, then you can write down the dp by dt is equal to Po by Qo into dq out by dt. Okay, use this expression. So that I can write now Q in minus Q out equal to V into d rho by dP to PO by QO into dQ out by dt. Okay. Here in this equation, we will represent this total term V d rho by dP into PO by QO by a term or a constant called TV, dQ out by dt. Now here this term d rho by dP is a known quantity. That is how the density varies with the pressure. This is the rate of change of steam density with pressure. This is a known quantity, therefore, all these terms are known. PO is known, QO is known. Therefore, this coefficient will be represented by a constant TV, right, and ultimately we will see that this becomes the time constant of the vessel. Okay. Therefore, now I have a simple equation, a first order differential equation. This Q in minus Q out equal to TV into dQ out by dt. You take the Laplace transform of this equation, okay, and then you can express the Q out in terms of Q in, right, and you can write down the transfer function in this form, Q out by Q in equal to 1 over 1 plus h times TV. A simple first order transfer function which we have obtained here for this vessel. Okay. Now, these are the Laplace transform variables, output input, and this TV is the time constant of the vessel. Okay. Now, you understand actually what are the parameters which determine this time constant TV of the vessel. Because if you see it here again, TV depends upon the volume of the vessel. Bigger the vessel, right, more will be the time constant. It will also depend upon these parameters. What is the QO for a given value of PO, and this quantity, that is the property of the steam. Okay. Therefore, with knowing these quantities or these parameters, this TV can be computed. Now, let us come to the actual turbine representation, now steam turbine representation. So far the steam turbines are concerned, we have different configurations. It all depends upon the rating of the machine, right. Now, this block diagram represents the simple tandem compound single reheat steam turbine. Now, here the basic blocks in this tandem compound single reheat steam turbine are that we will have control valves and steam chest, that is the control valves, right, and the position of the control valve is adjusted by the governor. Okay. The governor controls or speed control mechanism, right, they will be adjusting the position of the valves. Okay. Therefore, first block diagram which I can show here is control valves and steam chest. These valves are enclosed in a enclosure, right, which also houses some substantial amount of steam, right. Therefore, we call this a steam chest. The steam from this through this control valve enters the high pressure section of the turbine. After developing some power in the high pressure section, the steam temperature and pressure reduces, it gets expanded, right. Therefore, it is sent to reheater. After reheating, the steam is in the superheated condition again, and then it enters the next stage of the turbine. This is called the intermediate pressure turbine section, IP. the stream leaving from the intermediate pressure section enters the low pressure sections through crossover pipings, okay, and then it is exhausted to the condenser. Now, in this schematic diagram, we have not shown certain valves which are provided in the system. For example, I have not shown the interceptor valve. There is the interceptor valve provided actually here in the reheater circuit. That is the steam leaving the high pressure section, there will be an interceptor valve we call IV. Similarly, we have here a control valve which we will be showing, but along with the control valve there will be stop valves also. Therefore, there will be always two valves, stop valve which will be used to completely stop the flow of steam. Similarly, along with the interceptor valve also we have a stop valve, right. Now, in this models which we will be developing, we will not be representing these stop valves. Similarly, I am not showing here the interceptor valve, but they can also be represented. Okay. Further, depending upon the size of the machine, we may have a single stage reheating or two stage reheating. In case it is a two stage reheating, we will have one more section. Then the first section is normally called VHP, the very high pressure turbine section. Next will be called high pressure, then intermediate pressure and so on. That is the steam which leaves the very high pressure section, and after working, and when it leaves the very high pressure section will enter the reheater, again it comes out, enter the high pressure, when it leaves again it enters into the reheater and so on. Therefore, it is called two stage. Sometimes we have other configurations which are called compound configuration. There here you will find that all these sections are mounted on the same shaft, that is high pressure, intermediate pressure, low pressure and then generator. But in the compound type of steam turbines, they have two shafts, right, and but both these turbine sections are controlled simultaneously, right, they are not independent. If they are independent, then they become actually independent steam turbine sections. Okay. Now, our interest is to develop the transfer function model relating the power output from the turbine, and the turbine output is denoted as mechanical torque or mechanical power. Okay. And valve position, that is what is the position of the valve, right. Therefore, we will relate the mechanical torque to the valve position. That is, suppose at time t equal to 0, if I change the position of valve, right, then how the output at the shaft will vary, right. Now, you can easily see here now that we have control valve and steam chest. Therefore, this is a steam vessel, you can call it. High pressure section is also a steam vessel, because here we have two types of blades, stationary and moving, right, and the steam expands in the nozzles which are formed in the each section, right. Therefore, this also behaves like a vessel. This also behaves like a vessel, this also behaves like a vessel. Therefore, we can represent each of these by a time constant, and the time constant will depend upon what is the volume of these, what is the pressure and other parameters. Okay. Further, suppose actually the total power is generated, a total say mechanical torque developed is say Pm. Now, this total mechanical torque is developed in these three sections. Okay. A part of it is produced here in the high pressure section, half part in intermediate pressure section, part in the low pressure section, right. And generally you find that around 70% of the power is produced due to the intermediate pressure and low pressure section, and about 30% is produced in the high pressure section. Therefore, we have to account while modeling the fraction of the power which is produced in each of the sections. Okay. This is the simplest transfer function model of a single reheat tandem compound steam turbine. The configuration of that particular tandem compound single reheat steam turbine we have just now seen. The first block diagram, this one, this represents the steam chest and control valve. The time constant associated with this is TCH. CH stands for the chest. Okay. A certain amount of power is produced, that is PGV stands for position of the governor valve. PGV, P stands for position, PGV depends the position of the governor valve. Even this governor valve position is calibrated in terms of power, right. Then whatsoever power is produced here in the, now this TCH will also include the time constant associated with the high pressure section, right. Therefore, this block diagram represents the vessel, that is the chest along with the high pressure. Therefore, the total is represented by time constant TCH. Then when the steam enters to the reheater, okay, now the reheater pipings, you can see the pipings are there, and it has capacity to store a large amount of steam, right, and therefore, associated with the heater is a time constant called TRH, right. Therefore, we represent this reheater separately as 1 upon 1 plus S times TRH. And at the end, the steam which leaves the intermediate pressure, because this reheater along with the intermediate pressure is also that any time constant associated with the intermediate pressure is included in the reheater. Then at the end we have crossover pipings and the low pressure section. Therefore, we represent by one more time constant called TCO. CO stands for the crossover pipings, right. Now, at this point some power is generated in the high pressure section. If I call this power as PHP, okay, the power which is produced here in the intermediate pressure section, I will call it as PIP, and power which is produced here in the low pressure section will denote by PLP. Okay. Now, the total power which is going to be produced will be PHP into FHP plus PIP into FIP to PLP into FLP, and the total is PM. Okay. This is what is the, therefore, now we have a complete transfer function relating the mechanical power PM which is developed by the steam turbine and the governor valve position. In case you have another configuration, instead of having single reheat, if you have a two stage reheat system, right, then we may have to add one more section, right. Therefore, depending upon actually what is the actual configuration, one can develop a transfer function relating the governor valve position to the mechanical power input. And for each of these sections we can write down the differential equations, because when we write the model, right, the model is to be written by writing a set of differential equations. For example, in this particular case there are 3 time constants, and therefore 3 differential equations will be required to describe the steam turbine. Now, the state variables in this case will be PHP, PIP and PLP. These are the 3 state variables, okay. And in this particular arrangement, if you want to study the small signal stability, then there will be the incremental changes, like the delta PHP will be the state variable, delta PIP will be the state variable. But when I am writing the complete nonlinear model, then these quantities as it is will become the state variables, and therefore, we will require the initial values to solve the problem. Therefore, whenever I want to solve the stability problem, I should know what is the initial value of this PHP, initial value of PIP and initial value of PIP. They are my state variable. Any doubt? Now, the terms associated were explained, I will just reiterate. PGV is the output power from the control valve, or we can even represent the output position of the control valve, but that is also expressed in terms of power, calibrated in terms of power. Okay. TCH is the steam chest time constant, TRH is the reheater time constant, TCO is the steam storage or crossover time constant. Now, here I wanted to just mention that out of all these time constants, the TRH, the reheater time constant, is the largest. Its value is around 10 seconds, 5 to 10 seconds, while this TCH and TCO, the time constants are of the order of 0.2, 0.3, like a fraction of a second, they are small, right. And when you see that the time constant TRH, a large time constant, right, then whenever you are trying to study the mid-term or long-term dynamics, right, then this model will have its effect on the stability. Now, similarly, FIP stands for IP turbine power fraction, FLP is the LP turbine power fraction, PM is the equivalent generator input mechanical power. That is the mechanical power input which we have been talking about. Now, the three differential equations which you can write can be written in this simple form. Three differential equations are, because there were three single order or first order transfer functions, for each transfer function you can write down one differential equation, d by dt of PHP as PGV minus PHP divided by TCH. Similarly, d by dt of PIP equal to PHP minus PIP divided by TRH, and d by dt of PLP equal to PIP minus PLP divided by TCU, and the mechanical power PM is equal to PHP FHP plus PIP FIP plus PLP FLP. Okay. Now, these three differential equations, right, will form the model for the steam turbine. And if you go for slightly can say more detail, no, not more detail, but for different configuration, you can write down the number of equations required to describe that particular configuration. Now, let us see what is the sum of these three terms. Now, these three fractions, that is the fraction of power which is generated in the HP section plus fraction of power which is generated in the IP section and fraction of power which is generated in the LP section, this sum should be equal to 1. Okay. Now, we will discuss the speed governor for steam turbine, or we can say that speed turbine control, steam turbine control. Now, before I go into the details, I wanted to specify here, mention here that over the years there has been lot of development in the governing mechanism and the associated controls. Originally, the mechanical hydraulic controllers are used, they are still actually in operation, but these days they have what we call electro hydraulic controllers or electro hydraulic governors. But remember that in all this, the hydraulic servo motor plays very significant role. Now, when we look into the control for the steam turbine, the main function of this control is to open and close the steam turbine valves. This is the end objective, that we want to adjust the steam turbine valve position so that the required amount of steam flows. This is, and these valves have to be opened against the pressure of the steam, and their inertia and their weight is very substantial. The NTPC engineers know actually that their weight may be in terms of few tons. Am I right? And therefore, to make these valves to move, you require huge amount of torque or pressure, right? And therefore, this pressure amplification is done in hydraulic servo motors. Required amount of pressure amplification is done in hydraulic servo motors. Therefore, here the basic components of speed control mechanism can be looked like this. We have a speed governor. First block is the speed governor. Input to the speed governor is the speed, actual speed of the machine. Then the output of this governor will be the speed governor position. Okay. Depending upon actually the speed, there is some position of the governor. This enters into the first block here called speed relay, right. I will discuss these components separately, but there is a speed relay. To this speed relay we have two inputs coming. One is the governor speed changer position, another is the speed governor position. Because as I have told in the beginning, the first block diagram which I had shown you, that there were two inputs coming, one coming through AGC, which is the speed changer position, where you sometimes you can use that instead of speed changer position, actually the power output position, actually your reference, what the set point you can call it. Okay. And this set point can be adjusted by the AGC automatically, otherwise it is done manually. And another signal coming is through the governor. These two signals enter the speed relay. Speed relay is comprising of a pilot valve and a servo motor. Then there is one more servo motor, hydraulic servo motor, to amplify this power, and then we have the governor control valves, and output will be the valve position. Therefore, you can easily see here that input to this control mechanism we have two signals, one is the speed, another is the speed changer position, and the output is the valve position. Because when I talked about the steam turbine models, right, the input to the model is the valve position, right, and now in this particular case the input will be the speed and the set point. They are the two inputs. The governor which senses the speed, right. This is the mechanical speed governor, fly ball type of mechanism, and although there is a lot of developments which have taken place in sensing the speed, still fly ball type speed governors are in operation. NTPC people, is it operating in your system now or replaced? Therefore, now we use what is called actually the electric sensors, speed sensors. We call it, for speed sensing, instead of using this mechanical fly ball type of arrangement, we use actually the electric speed sensors. Basic simple, actually you can use a permanent magnet generator, PMG, and the speed can be sensed by knowing the voltage output of that. Okay. Now, here irrespective of what type of, you can say, the speed sensing you use, right, we have a signal which is proportional to the speed. Okay. Now, this diagram shows a simple speed relay pilot valve. Now, when I talk electro-hydraulic governor, right, the mechanical hydraulic governor or controller, the M is replaced by E. Therefore, basically the speed sensing mechanism is replaced, but so far processing is concerned, still we have this speed relay and servo motor, hydraulic servo motor, right, because the amount of power which is required is enormous, the amplification is very high level. Okay. Now, in this arrangement, I will just show you here actually this arrangement. If you see this rod which is coming here, that represents the position of the speed governor. Now, when this rod actually is attached to a lever like this, and this lever is attached to a pilot valve and a spring loaded servo motor. Now, here actually you will see a very interesting thing, that always whether I talk about hydraulic servo motor or a pilot valve, right, there will be a linkage between the valve piston and the servo motor piston. This linkage is basically to provide what is called negative feedback. This is a negative feedback always. Now, the arrangement is very simple here. The high pressure oil is here, it is maintained, right. When the pilot valve, suppose actually the pilot valve is made to move down, okay, then this high pressure oil will move into the servo motor and push the piston up. The movement of this piston when it is moving up is actually restricted by or controlled by the spring pressure. Okay. Now, you can easily see that when this is trying to move, this will also come down, while at the same time when this oil enters and tries to push it up, through this same mechanism this pilot valve is also pushed up. Therefore, this acts as a negative feedback. Now, of course, here in this diagram it is shown actually that as if this servo motor is controlling the steam valve, but in case we need one more stage of amplification, then this rod or this piston is going to control the hydraulic servo motor. In this hydraulic servo motor, again the similar arrangement is there. You have this pilot valves, high pressure oil comes here, right, and this linkage shows actually the connection to speed relay, right, and you can easily see actually that when this lever moves up, right, this pilot valve goes up, it opens this and the oil can come down. When it opens, what happens is the oil will come down from this side and it enter from the top, right, in the sense that it is moving down. So, that is actually when you move it down, the oil will come from the end, oil will leave from these two sides, but enter through the high pressure section only, and it will move from the top, push it down, and oil will come out like this. Therefore, through this mechanism, the hydraulic servo motor actually you will be, because of the high pressure oil which is maintained, right. Therefore, this power amplification takes place, okay, and the amount of amplification will depend upon what is the cross section area of the hydraulic servo motor or piston, right, and what is the pressure which is maintained in the high pressure oil, right. These are the parameters which will determine. Now, when we try to develop the model for these devices, we have to look into two aspects. One is that the movement of this piston for a certain particular opening will depend upon the flow of oil at a certain pressure. Therefore, this movement can be considered to be a function of time. As the time passes, it increases. Therefore, basically this can be represented by an integrator. It will represent, because when the oil is flowing at a certain rate, the piston will keep on moving, right, the position will keep on changing. Further, since in these all the devices there is always a negative feedback, so that output, whatsoever is the output position here, is fed back directly as negative feedback. Okay. Another thing which you have to see is the that there are two limits which we will be talking about. One is called actually the rate limit, that is the rate at which this valve is going to move up and down. Another is the position limit, upper and lower position limits, that is when this can go to the top, it can come down to the bottom. There are two limits. Okay. Therefore, there are two limits which will be shown. One is called actually rate limit, another is called the position limit. While when we talk about actually the speed relay, these limits are normally not required to be shown. Now, this block diagram represents the transfer function model of a simple steam for a transfer function model of steam turbine governor. Now, you can just start like this. This is the speed governor, input to this is the speed. Okay. Therefore, output of this will be a k times speed, that basically it is a speed sensor, speed deviation is going to be sensed here. Now, this is going to be compared with the reference, the error comes here. Now, this block diagram which I have shown here, this block diagram, it represents actually the transfer function of the speed relay. It is something like this. Speed relay, we represent the time constant of this as TRS or TSR, not RS, TSR, I can put it, you can call it TSR, speed relay, and integrator. This is basically the integrator. The position is fed back, there is a negative feedback loop here. Okay. And this is a plus, this is minus. Now, this can be replaced by an equivalent transfer function of the form 1 over 1 plus S times T S R. That is, this transfer function which has actually, which represents the integrator and a negative feedback, is represented by a first order transfer function of this form, right. Similarly, here actually is the transfer function of the servo motor. While in the servo motor we try to represent the rate limit and the position limits, and therefore, this is the time constant 1 upon TSM, servo motor time constant 1 upon TSM. At this point we can sense what is called the rate, and after integrating we can sense the position, right. Therefore, these two are provided. Then here you will find actually there is the control valve movement and actually the servo motor movement, there is a non-linear relationship, and therefore, this is the valve characteristic. Now, in order to linearize this, we put actually a cam which will have a characteristic opposite to this, so that when this put together it will be linear characteristic. Now, this is the complete transfer function model of a steam turbine governor. Now, here I have not shown actually in this diagram, but the speed relay output can be used to control other valves also, because you may have, for example, the interceptor valve. Interceptor valve can also be controlled through this speed relay, that is why it is on other valves. Okay. Now, using, because for stability studies we can model this non-linearity, this non-linearity can be modeled, and we can write down the transfer function or the differential equation relating the output of speed relay to the input. Similarly, we can relate the output of the servo motor to the input, and these relations are available. Therefore, we can write the complete mathematical model of the, and you can easily see that this CV which I have shown here, control valve position, is basically the PGV, the governor valve position or control valve position, they are same. Okay. Now, with this let me summarize our presentation today. We have discussed today the transfer function model of steam turbine and steam governor, steam turbine governor. We have also developed the differential equations which can be used to represent the steam turbine and the differential equations to represent the steam turbine governor. Okay, thank you.